Okay, this is my talk on thermodynamic displacements and phase equilibrium. Alright, so I'm going to start off with a couple of definitions. First, a virtual displacement is a change within an isolated system when the independent variables are held constant. For example, if you're using Gibbs energy, the independent variables would be temperature and pressure. Also, all virtual displacements are extensive quantities and are denoted by delta right there. In my I will define equilibrium when the entropy is at a max and the change in entropy equals 0. And this can always be also thought of as what to do when there's holes in a piston when you talk about thermodynamic systems. Okay. All right, my fundamental equation. First, you start off with the most general sense. You have some function is equal to a constant. In this case, it's 0. And then I'll pull out the entropy, and that will be a function of internal energy, volume, and number of moles. So, in my so what I'm doing here is I have the first law of thermodynamics right there, and then I'm going to pull out the entropy term till it's on that side, and then I'm going to divide everything else by T to get this equation. And this one is why I use the entropy to define my equilibrium conditions. Alright, now I'll start with my system. It's going to be an isolated system with two subsystems. Subsystem 1 is right here, and the second one is right here. When I say it's in thermal, mechanical, and material property, that means the heat can travel back and forth to two systems. The piston right here with the holes in it can move back and forth, and the material can move through the little holes in the piston there. And then the total energy of the system is just the addition of the two subsystems right here. Okay, now the virtual displacements. I'm just going to change the delta for everything. And so now it's in terms of the virtual displacement, and at 0, it's equal to 0. Alright, now I'm going to use my equation that I derived earlier, and then for the total system, it's going to equal the sum of everything that from the first subsystem plus everything from the second subsystem will equal a change of the total system. Since it's an isolated system, we can reduce it to this form, which is entropy. And we're going to set it, this has to equal 0 at equilibrium. So once we're at equilibrium, that means all these three expressions have to be equal to 0 for the change in entropy to be 0. That just implies that the temperature at equilibrium is equal to, and the pressure and the chemical potential. And this analysis we can provide for any phase system or phase analysis. And that's it for real simple, real quick. And at the end, this is one of my first attempt at PowerPoint, and it's a visual person down there, me. So if you have any, can you just leave any response or opinions and let me know what you think of this. Alright, I'll stop right here.